If you've not heard our previous episode, episode 5, you might want to pause this playback and listen to that one first. The two episodes together feature an extended discussion between Callum Chase and myself, David Wood, with AI researcher Aleksa Gordić from DeepMind. The two episodes each make good sense in their own right, but it's the combination that delivers the fullest understanding of what's going on inside the AI systems that are, these days, producing many astounding results. The AI systems that are poised to dramatically change more and more parts of human work and human play. The discussion in this episode picks up with something called DC GANs. It's not important to understand what all the letters in that acronym mean. The important point is that these systems were the first time that high-resolution graphics images could be composed by AIs out of their own artificial minds, with the output being indistinguishable from real photos or from pictures drawn by human artists. These systems had solved a problem called stability. When they added more detail to an initial low-resolution picture, it turned into a better picture with higher resolution, rather than degenerating into an unstable mess of pixels. But as we'll hear, that's only the story warming up. The conversation will lead into the particular power of combination approaches in AI. To be clear, Aleksa is speaking here in a personal capacity rather than representing DeepMind. Let's join the conversation. Welcome back to a continuation of the discussion with Aleksa Gordić, a remarkable communicator about what's happening in AI. And let's pick up the thread of what's happened to GANs. Aleksa.
Cool. So I think we stopped with the DC GAN, right?
Yeah.
So the deep convolutional generative adversarial network that you said, I think that Jan LeCun said that was one of the biggest breakthroughs back at the time. So I think that network was published in 2015 or 2016. And what was so special about that network is that that was the first time that we could generate high quality, high resolution. Well, not that high quality, but high resolution images. Before that, we were kind of constrained to, in the original paper, I think it was 32 by 32 pixels, which is laughable, especially looking back from the 2022 perspective. So what was so big about that model, the DC GAN model, is that it made the GAN training stable. GANs are notoriously hard to train. So they end up having various issues such as so-called mode collapse. And that's just a fancy way of saying there is some particular class of your imagery that the model is dropping. So that means it cannot generate cats, even though you did train it to generate cats. And so it drops so-called mode collapse. And then even more severe mistakes such as the model not converging and learning anything. And so you just end up with like a noisy image, nothing interesting pops out. And so DC GAN basically was the first GAN architecture that introduced the convolutional layers, the so-called batch norm, and some other layers that helped stabilize the training and made it higher resolution. And yeah.
So we don't need to explain what is particularly deep or convolutional about it. We just need to say that there was some clever innovations that addressed problems of instability and what you said, which resulted in not just 32 by 32 pixel drawings, but higher resolution drawings, which more accurately, more often represented what people were hoping to see.
Exactly. And back to 2020, we have images that are like at least 1,000 by 1,000, and you can go even much bigger than that if you use some techniques such as outpainting. So like OpenAI recently released this outpainting with DALL-E 2 technique, where you can just take your image and then, well, what the word says, start outpainting and imagining what that image would look like if you go outside of the frame of the initial image.
What's the value of doing that? Don't you end up with painting that's invisible?
No, the model learns something interesting about the visual world. And once you condition it on the part of that image and the rest is black initially, right? Because you're outside of the reach of the original image, the model can imagine what a reasonable continuation would be, and then you just keep on increasing the resolution.
So it builds a better and better model even if it's building it with elements which are never going to appear in the image.
Well, it's building the bigger and bigger image. The model is kind of fixed. You train it and you don't touch it, and then you just use this outpainting technique to generate bigger and bigger images.
It's almost like a human might do. If you showed them a bit of a picture, they would rely on their knowledge of how the world looks, and they say, well, in that case, if we go further up, there's probably a sky.
Exactly.
And there's probably a sun up there. And I can see a bit of a branch of a tree. Maybe there are some leaves to be added on. So that's our model of the world. And somehow there's something similar in these grand models that have been built.
Exactly. And it's not only the visual, those image generation models, it's also the text generation models. So models such as GPT-3 or any transformer, really. So you can prompt it with a piece of text, and then it can continue on. That's how you can use it to generate stories. And there were interesting applications that popped up using some of those transformers in the background. One of those were AI Dungeon, where people would literally, they could create stories on the fly where you input a particular sentence to the model, and then the model forms a story, and then you start interacting with the model. You can have dialogue. So all of that thanks to that type of potential to model the world.
It's probably time to move on from generative adversarial networks onto these splendid new diffusion models.
Yeah, those are interesting. So the first one appeared in 2015, but nobody picked it up. Like it was literally just staying there on the shelf somewhere, and nobody was making anything useful from it. And then I think in 2020 came the paper called DDPM. I think it stands for Denoising Probabilistic Diffusion Model. Okay, I completely butchered it, and I even have an explanation of the paper on my YouTube channel. But all in all, that's a diffusion model that made it practical to train that new class of models. You can think of it as DC GAN for GANs. So what DC GAN has done for GANs, that's what this DDPM paper has done for diffusion models. And so they operate on a different set of principles, but the cool thing is they don't suffer from the mode collapse problem that GANs did suffer from. And they are more stable, but there are also some downsides. So the downside is they are much more computationally intensive. And you do have to do, for example, like 50 passes through the neural network in order to get your result, as opposed to GANs, which you just do a single forward pass, and you end up with an image generated. You also have to weigh the upsides and the downsides.
Well, if they're more computationally intensive, why are they sweeping the field?
Because they're so better. They're stable, they generate better, higher quality results, and we do have compute in 2022, so we can afford to train it. And then there was, maybe you recently heard of stable diffusion. They kind of mitigated some of the problems when it comes to computational requirements because they are training in the so-called latent space. That's like a synonym for, I guess, hidden space. But so you basically embed your image into some smaller dimensionality, and then you do the diffusion inside of there, and then it's cheaper to train it when you're in the lower dimensional space.
And what does this word diffusion mean here? I think of diffusion from chemistry experiments. You put some water on one end of a bit of cotton wool and it diffuses to the other end. Is there anything similar in these diffusion models?
I guess there is some similarity with that example you gave, but the diffusion here was inspired by diffusion processes from, I guess, physics. So what I do in this particular example is you take an image and you gradually start adding the noise on top of that image until you end up with a completely noisy image. And that would be referred to as a forward diffusion process. It probably makes intuitive sense why it's called diffusion now. So because you kind of go in that forward process and you kind of destroy all of the information in the image. And so what this class of models does, it learns the reverse process. So it learns how to go from the pure noise into the image space. And that would be literally what they do on a very high level. Yep.
That sounds really remarkable. That sounds like rewinding entropy. I mean, when you make something more diffuse, you lose the shape, you lose the pattern. And to reverse engineer that sounds really hard.
Yeah, as I said, they do require a nice amount of computational, they have higher computational requirements. But with those tricks such as latent diffusion models from behind the stable diffusion, we can also mitigate some of those requirements.
And I guess it's used in what's been seen recently. Old photos with low resolution taken in 1830 have been fed into this, and now they look like a photo that could have been taken in 2022.
There are so many things you can do with these models. For example, you can create these so-called semantic segmentation masks, where you literally have just like an image. that has, for example, the sky is colored blue, but you just have a blue blob, nothing else. And then you maybe put, for the hill, you put a green color across a part of the image, but that's just a green blob. And then you put maybe, I don't know, like sea on the bottom or something, I don't know, some type of such information. And then once you feed that image into the model, it can just imagine, but under those constraints. It will obey those constraints. It will be creative, but within the constraints you gave it in that input semantic segmentation mask. And so you can now go even further than that. You can do bounding boxes where you just have a bounding box in a particular class, and the model will generate an object of that class, and that object will be inside of that bounding box. So you can kind of go berserk here.
If you do that, what you just suggested, and you create an image with blue at the top for the sky, and then say kind of a turquoise sea in the middle and green grass at the bottom, and then the machine will create a photorealistic image of a scene. It might add some trees and ships and things. Is it doing that by reviewing all the images that are available on the internet and saying, oh, I like that one and I like that one, and stitching bits together? Or is it doing it de novo? Is it creating a new image that's never been seen before, not just by combining other existing images, but by imagining something completely from scratch?
The latter. So the latter is what it's doing. So it has all of the knowledge it needs in the weights. So it never accesses the internet. It doesn't call the browser APIs or whatnot. So it just creates everything de novo, as you said. But in order to do that, you had to, during the training, feed it with a lot of images. And yeah, these models usually are also trained with so-called image text pairs. And then later you can condition them on text. So you can be very crazy now. You can say something like a hedgehog in a Christmas jacket walking a dog on the leash.
There's some great things. I saw an image today of a couple of teddy bears developing an AI system underwater using equipment made in the 1990s, and it was fantastic.
Exactly. You can go really wild and just be very creative. Again, there are failure modes. It's not perfect, but I think it's mind-blowing where we are if you have any historical context of how hard this task was historically.
Yeah.
And is it fair to say that when error modes are discovered, and people are pointing out the error modes with glee sometimes, quite often it just takes a little bit more time and the errors no longer occur, either by applying more scale or by tweaks to the algorithms in the ways that you've described?
Well, historically, if we extrapolate, that's exactly what's happening. Like we see better and better performance, we see less errors, but they still exist and there are many problems. But yeah, historically, if you extrapolate, the models keep getting better and better. And that's what we all benefit from.
We'll be right back after a quick break.
The People in Performance podcast offers insights into the strategic competencies, behaviors, and results needed to increase the performance of employees and leaders. The show looks at all areas of the world of work, including attraction and recruitment, onboarding, training, and succession planning. Tune in to get a better handle on the stages of workforce planning you need to master in order to guarantee long-term success in a rapidly changing world of work. New episodes drop each week. Check out the latest People in Performance episodes on your podcast platform of choice. Follow us on socials and read the latest articles at pppod.com.
I saw a blog post by Scott Alexander recently. I'm not sure whether you noticed it. He was pointing out that people had complained about these image generation algorithms because if you gave them an actual careful description that involved some mathematical reasoning or some logical reasoning, they would have something that had all the elements that were in the description, but they wouldn't always be in the right inferred order. But apparently, within 3 months, the systems have grown in capability to the extent that they're now making a much better job at logical deductions as well as just representing the individual images.
That's correct. But there are still failure modes. They are just harder to find. But that's where we get into the fact that we are still, as a field, working on improving them. And one of the examples that GPT-3 pointed to is that even when we had 175 billion parameter neural network, the transformer, the GPT-3, it was struggling to do, for example, 3-digit arithmetic. And if you think about it, we shouldn't even be surprised because they were trained to do the next token prediction. It's kind of remarkable that we get even machine translation for free. We never trained that model explicitly to learn how to translate from one language from English to German or whatever. And we also never taught it how to do summation. and it somehow learns anything at all. And I think that's the first thing that's kind of remarkable. Now, the thing I mentioned with the arithmetic, there are subtle problems where I would have to go into some technical details, like tokenization, for example, because when you feed the number into the neural network, into the transformer, for us humans, when we're doing a two-number addition, we have two entities. We have two numbers and we have the plus operator. The neural network just sees that as a piece of text, and it might end up splitting that big number into multiple chunks. And so you end up with a single number, for example, 328 being split as 3 and 28. And then you feed that as two tokens. And so because of those lower level details, the network is not well suited to solve that type of problems. I think it's quite a surprising phenomenon that we have decent 2-digit and single-digit and some performance on 3-digit. I'm talking now about 2020s. 2 years later, I'm fairly sure I'm not completely familiar with this particular problem for just pure arithmetic, but I'm fairly sure we are much better at this already now.
I have the impression that people like you at the cutting edge of this technology are often taken by surprise by the next thing that the machines are able to do. Is that true, or are you able to tell us, if it's allowed, for instance, what they will be doing next year? Or do you think you might be surprised by what they'll be doing next year?
We definitely all get surprised. If I am not surprised, that means it was predictable. And if it's predictable, that means I can predict the future, and that's kind of hard. So that would be a TLDR. It's kind of hard because there are so many research labs and companies and people working on this, and it's like a hive mind. And a lot of cool things pop up, and you never know where the next idea will come from. And so we definitely all get surprised. There are some patterns, like, for example, we did have suggestions that from previous papers that scaling the models from like 1 billion to much bigger models will give us results, because we saw that there was no saturation going on when you look at the performance and the loss metrics. But yeah, you cannot precisely predict what's going to happen, obviously.
It seems to be more disjunctive than a lot of technological development. In the car industry, they can tell you, broadly speaking, what a car will be doing in 2 or 3 years' time. Somebody's working on that, and you know roughly what it will end up as. But in your field, a lot of the improvements seem to come completely from stage left and are absolutely surprising.
That's true. And the nice thing is some of these ideas literally come up from a couple of students working in some university. For example, diffusion models didn't come out from, as far as I know, because you did not need that much compute for the original diffusion models. And so those ideas can pop up anywhere.
And wasn't it the case that GANs was just sort of brainstorm one evening, and the person went home, Ian Goodfellow went home and said, well, I'll try it and see what happens, and was surprised himself at how good the results were.
Exactly. That's precisely what happened. So he had a couple of beers, in his own words, and he came home, coded up the initial prototype, and apparently it worked pretty much out of the box. But it was a very low resolution, just like a proof of concept type of a thing, which was already remarkable.
Can we ask you about some of the slightly older ideas in AI and whether they're all dead now? Both Callum and I have read a book by Pedro Domingos called The Master Algorithm, in which he says there's multiple tribes in AI, as well as the kinds of things we've been talking about. There are evolutionists and Bayesians and analogizers, and I forget what they're all called. So are these all dead?
Connectionists and symbolic AI folks. I think those are the 5 tribes.
Yeah.
That sounds good, yes.
To be honest, I'm not completely familiar with that book. I haven't read it, but I read a couple of things that he had to say on that topic. So you were asking, sorry?
Are all these ideas overtaken, or is it likely that some of these tribes have still got contributions to make to the future of AI? Are they all still punching and alive?
Personally, I think that we should nurture various parallel, even completely non-overlapping research directions, because you never know ultimately what ends up being the right approach to engineer intelligence. We were discussing the AlexNet moment in the previous video, 2012, so we had 10 years. So that's where the connectionist, quote-unquote, tribe has been giving the most results, arguably. So transformers, GANs.
The connectionists are deep learning.
Yeah, exactly. When you say connectionist, you mean on artificial neural networks, deep learning, etc. Yeah, that's correct. I actually read on that idea today. The problem is that taxonomy is kind of blurry sometimes, because oftentimes you combine, for example, when you do evolutionary search, you use deep neural networks sometimes to solve some problems. And so it's always interconnected ideas do go into the different brackets. You know what I mean? Also, the ideas from the symbolic, the good old-fashioned AI, also are propagating, and we see them even today in our deep learning models. So, I don't know, like arguably you can say that transformers, because they deal with these discrete tokens, depending on how you define the word symbol, you can think of that as symbol, and then the transformer is basically a neurosymbolic model. That might be a stretch. It really depends on your definition of the word. And then you have models such as AlphaGo from DeepMind. That was back in 2015, won against Lee Sedol, the biggest Go player in the history. And that model literally uses a combination of symbolical approaches where you have some if-else statements, so some code that had to be written by a human being, and then you had like a call to a neural network that would be the intuition part of that system. And so it's literally a combination between symbolical approach and the connectionist or deep learning approach. So it's very blurry. There are no clear distinctions, I would say. We obviously kind of abandon, at least the mainstream researchers did, the pure so-called expert systems where you just had basically if-else statements, knowledge bases, and there was no neural networks. You were just trying to encode the knowledge you have as a human or as a group of humans into the computer and try to get that to work using some logical rules, etc.
This is when they would take a lawyer and say to the lawyer, what would you do in this situation? And then what would you do in that situation? And try to imagine all the situations the lawyer might ever encounter, feed them all into a computer, and then that computer would have the knowledge of the lawyer and be able to act as a lawyer. And it never worked because the edge cases were almost infinite. There's always another case which you haven't thought of, which you then have to do. There's a project ongoing called Psych, run by a man called Doug Leonard, who's been doing this for 30 odd years, this same expert learning education process. And I heard him on the Lex Friedman podcast recently saying that it's working. But he seems to be a lonely figure, and I don't think anybody else believes it really is working. I'm
not really familiar with his work, but yeah, there are problems such as at least those older systems. I'm not sure whether those systems evolved in the meantime, but those older systems literally required a bunch of experts to encode the knowledge, and it's not robust. You cannot evolve. Like that system cannot learn. There is no learning component, and that's what it separates it strongly from machine learning. The original chess algorithms used to work that way. Like the famous Deep Blue that won against Kasparov was the symbolic approach and was like a brute force algorithm trying to basically roll out the games of chess to the very end and then try and find the optimal next move given the current state of the board. And those were the symbolic. But the problem is they can only be as good as humans. Whereas if you take AlphaGo, at least later iterations, AlphaZero and then Mu0, can learn in the so-called self-play mode, where they literally don't need any human data. They just play games against each other. And that's why like Lee Sedol and other Go players were surprised by some of the moves. I think one of the moves was like the move 37. It's now even famous move 37, where they were surprised. They were caught by surprise. They were like, okay, why is the machine doing this? Is this a glitch? Is this a bug? And it turned out it was just a creative move. And that the model at that point thought that that's the best thing to do. People nowadays are learning from those systems, for chess especially. Like we know that professional chess players such as Magnus Carlsen and others are leveraging those models precisely because they don't have the hard-coded knowledge from other humans.
It's quite extraordinary that a game which humans have been playing for 3,000 years and a machine comes along and overnight unveils an entirely new way of winning the game, an entirely new strategy to follow, which nobody had ever thought of, no human had ever thought of. That's a truly remarkable development.
Oh, 100%. I agree with that. I mean, for me, it's beautiful that these systems are basically challenging our worldview, and they're teaching us and showing us what's hard and what's actually not that hard. So like historically, chess was considered as the pinnacle of human intelligence. Like that's the hardest problem. We'll never solve chess. We'll never solve Go. Go is even more complex than chess. And then stuff like vision, grabbing an object and picking it up from the floor, all of that is kind of trivial. Anybody can do it, right? And then it turned out it's completely opposite. We solved chess even with those simpler brute force approaches. Go was not easy not to crack. We did have to deploy the neural network approach, but it's kind of fascinating that we are now discovering what's actually hard to program into a computer as opposed to what we thought was hard.
This is Morevich's law, isn't it, after Hans Morevich? The things that we find hard are sometimes easy, and the things that we find easy are very hard to program into a machine. It's interesting that you say that the cutting-edge AI systems are using a mixture of deep learning but also symbolic AI, because that's something that people have been saying for a long time needs to happen, that deep learning won't get us all the way to artificial general intelligence and superintelligence on its own, but it's already happening that the different approaches are being merged. One of the things that people wonder about is, as these systems get better and better, is it inevitably the case that they will use more and more compute? Or is it possible to keep finding ways of doing it more efficiently so that you ratchet down the amount of compute before you sort of build it up again and need to ratchet it down again? Is there any evidence as to where that will go? Will we always be able to find more efficient ways and reduce the compute so it isn't just Google and Microsoft who can play this game, but ordinary mortals can as well?
Let me see how I can take this one. Basically, if you just think about it, if you compare the scale and the computation that's happening in the human brain, and you compare it with even the biggest systems we currently have, it's so much bigger compared to what we have currently. So the problem is our current systems, our hardware, which is usually general, like GPUs, are not AI-specific chips. They are not dedicated to do that particular task. Well, they're not as efficient as human brain. And also, you can argue like brain has sparse component to it. You don't activate all the time every single parameter, whereas when you do a pass through the transformer, you activate all of the parameters in the transformer, unless you're dealing with these sparse or so-called mixture of experts, MOE models, which sometimes go above 1 trillion. So we do need both the algorithmic innovation, we need the hardware innovation, and efficiency will increase. I'm fairly confident that we will, in like 10 years, be able to perform the same type of computation for much less electricity consumed, etc., etc. But I also strongly believe that, and that's just my personal take on this, is that like if you just think of it, like human brain has roughly, I think the average number that's being thrown around is around 80 billion neurons. And that's neurons. That's not number of parameters, because each neuron, on average, again, this is a number I've seen in the literature, is around 10K, so 10,000 connections. So now you multiply the two, and you get some huge number that's, I think, at least 1,000x, if not like million x bigger than the biggest models we currently have. And so I think it's only reasonable, because we still don't see the saturation looking at the scaling laws, to try and scale it up to even bigger sizes. Now, I do agree there are many problems with that, like ecological issues. And as I said, as the time progresses, we'll have better and better hardware. We'll have dedicated chips. Various companies are working on AI accelerators. And so my hope is that as we are scaling more and more, that the hardware will also be picking up and that we'll have more and more efficient systems. And it's not only GPUs and TPUs. People are working on like neuromorphic devices, analog computers. There are companies such as GraphCore working on systems where they support much more naturally sparse computations. You have Cerebras where they have literally one huge chip where you can train GPT-3, in their own words, on a single chip. Whereas I think it took 10,000 GPUs, V100s, to train the original GPT-3. So we are advancing on multiple levels here. And my hope is that we manage to keep up increasing the efficiency and improving the hardware. And at one point of time, we'll be spending maybe even less than now, and we'll have much more compute and much bigger scale.
Is there an idea that we will train quite general models very extensively, and then it'll be easy to retrain these models or tweak them or customize them for particular tasks?
That's what happens in practice, pretty much. Like big companies mostly share the weights, the pre-trained models, and then many other humans, even individual researchers, can take that model and just fine-tune it. And that requires much less data points to fine-tune the model on a particular downstream task. And when I say fine-tune, what I mean by that is just additionally train it on a particular novel task. For example, you take the GPT-3 or something. Well, GPT-3 is not publicly released, but you take some recent large language models that have been published, are Open Pre-trained Transformer from Meta or Bloom from Big Science. All of those are 175, 176 billion. And then you just train it additionally on, for example, question answering or machine translation or whatnot, depending on what you care about. That's the current trend.
I think we have to wind down this conversation, Aleksa, but maybe you could give a few thoughts on what else should people try to learn about. I know there are many other terms that are in this discussion on breakthroughs of AI. So there's things like neural style transfers. There's things like chinchilla and flamingo and gato. So are there things that people should try and read up about, and maybe Callum and I should feature in future episodes?
There are many interesting things, depends on your interests. Like there's also the NERF model, you might have heard of it, the neural radiance fields. And the idea of that model is to take a 3D scene, and so a visual 3D scene, and basically encode that 3D information inside of a multi-layer perceptron, so just a type of neural network. And then what you can do, you can query from an arbitrary direction that 3D scene and basically render an image. So that means you can now smoothly go across the whole scene in the 3D space, and even though your training data was maybe 50 images of that scene, now you can basically predict what that 3D scene would look like from any other direction. So that's one additional interesting thing that people might be curious to find more about.
So you can have an image of somebody from the front and the machine can figure out what they look like from behind, or make a good inference as to what would be a very plausible view from the back.
This NERF model would have also the images from the back, but maybe only a couple of them. Not from every single direction, obviously, because there is obviously infinitely many directions you can choose. Yeah, neural style transfer, all of those are interesting. I personally was involved around the Flamingo models. That's the visual language model that came from DeepMind. That's something that's very dear and close to my heart, and something I work on a daily basis, basically. So that's something you should read the paper, the Flamingo paper. Gato is super interesting. It's hard to pick a single idea because diffusion models are interesting, neural style transfer, all of that. Also, just techniques that lie behind all of these scaling efforts. Just learning how do we take a neural network that cannot be fit on a single GPU or TPU or whatever device you're using. Instead, you have to split it, so-called sharding, onto multiple devices, and then you have to have this dance between them, synchronization, such that we can train the model on a cluster of devices. I think there is a lot of engineering ideas, and I think that we've been discussing research a lot in this podcast and in the previous episode, but just engineering is also so underappreciated, and there are so many innovations happening there and on the hardware side, and so it basically depends on your curiosity what you want to explore next.
I can certainly see, Aleksa, why you're so excited about this. The enthusiasm beams out of you, and you've done a terrific job of making it much more accessible to the rest of us, so I thank you very much indeed for that.
Thanks, Callum.
Thank you from me as well. Thank you.
Thanks, David.